Hello, I'm Percy. We will learn about LCR circuits, also called RLC circuits. An RLC circuit is an electrical circuit consisting of a resistor, an inductor, and a capacitor, connected in series or in parallel. The name of the circuit is derived from the letters, where L is for inductance, C for the capacitance, and R is for resistance. LCR circuits have many applications as oscillator circuits. These oscillator circuits were used in radio receivers and television sets. LCR circuits can also be used as a band-pass filter, band-stop filter, low-pass filter or high-pass filter. The LCR filter is described as a second-order circuit, meaning that any voltage or current in the circuit can be described by a second-order differential equation in circuit analysis. Let's discuss on one of these formulas: resonance, natural frequency, damping, bandwidth, and Q factor. Let's start with resonance. An important property of this circuit is its ability to resonate at a specific frequency, the resonance frequency F0, which is measured in Hertz, and the other called angular frequency ω0, which is measured in radians per second. For each revolution, we can multiply by 2 pi, that is 2 pi radians per second. The formula can be obtained as ω0 equals 2 pi times F0. When this happens, resonance can be stored in two different ways. In an electric field as the capacitor is charged, and in a magnetic field as current flows through the inductor. Thus, the resonance frequency is defined as the frequency at which the impedance of the circuit is at a minimum. Next, for a natural frequency, the driven resonance frequency in a series or parallel resonance circuit has the value of ω0 equals 1 divided by square root of LC. This is exactly the same as the resonance frequency of an LC circuit, that is, one with no resistor present. Next, for damping. Damping is caused by the resistance in the circuit. It determines whether or not the circuit will resonate naturally. Damping can be measured in nepers per second. Nepper can be written as NP, a logarithmic unit for ratios of measurements of physical field and power quantities, derived by John Navier. The unit which gives us gain and loss of electronic signals, as in the case of decibel levels. The damping factor, a dimensionless unit denoted by zeta, equal to alpha divided by ω0, where alpha denotes as a damping attenuation. There are three cases: if damping factor is greater than 1, which is said to be overdamped, the circuits would not resonate. If the damping factor is equal to 1, which is said to be critically damped, the circuits would likely to be resonated. If the damping factor is less than 1, which is said to be underdamped, same way for the resonating circuits. Next, for bandwidth. The bandwidth is measured between the cutoff frequencies, most frequently defined as the frequencies at which the power passed through the circuit has fallen to half the value passed at resonance. It is denoted by delta omega. We write delta omega equals ω2 minus ω1, also equal to 2 alpha, where ω1 denotes as lower half power frequency, and ω2 called the upper half frequency. For a fractional bandwidth, we write BF equals delta omega by ω0. And finally, the Q factor. The peak energy stored in the circuit divided by the average energy dissipated in it per radian at resonance. Low Q circuits are therefore damped and lossy, and high Q circuits are underdamped. Q factor can be calculated as Q equals 1 by R times square root of L over C. So we have seen these formulas for the LCR circuits. If you like, you could see the miscellaneous ones. Like, comment, and subscribe now.